What you got?
So the gold particle, would it be able to also start orbiting, and would that
Yes.
increase?
Yes, it can. In fact, that's how we put it on the surface.
Okay.
We put it on the surface by drawing it in from an orbit with a little pulse of intensity so we could get it close enough to stick. Yeah, that's a very good question. Yes?
In the case of those rings that you talked about that
Yeah.
companies are developing,
Yes.
like-
Genolite.
yeah, so what are those rings actually?
Okay, so there's silicon, which is very high refractive index on silica. Silicon on silica. So silica has a refractive index of about 1.45, but silicon is way over 2. So the light is confined within the silicon ring. And then, of course, there's evanescent fields around the ring. Yeah, that's a very good question. Thank you. Yes?
About the microfluidic bead, of microfluidic cavity, does because it's like too small, so the physical feature will be like changed?
Of the,
Around the orbit, like,
oh, the orbit.
yeah.
You mean about light force fluidics, this new subject?
Because we know that like gold, when it's in like the nano size, the feature will be like vast change.
Changed. I'm not quite getting it, but the gold particle will be grabbed on to by the tractor beam, the light force, and be drawn to the surface. If there's a repulsion between the surface, as there was in the case of these negative particles and the negative surface, then it can remain out there and orbit.
And I'm quite confused about why you put a bump in it and then
A bump in,
on the surface, and then
Ah.
the sensitivity will be like
yeah. Okay, so the normal sensitivity of the bare cavity was not sufficient to see a single molecule. But when you put a plasmonic particle on, it has this property that at a particular frequency, and it's pretty broad frequency spectrum, there's a large field created on the north and south pole of this nanoscopic thing, okay? So that if you're sending a particular field in, you get a much larger field, and therefore remember that principle that I had, which the sensing principle said that the amount to which you polarize, the energy that polarizes the particle, is the wavelength shift of the photons in the mode. So if you have a higher field, you polarize it more strongly. I hope that helps. Yeah. Yes?
Is this biosensor available in market for any medical?
Sorry, I'm sorry.
Is this biosensor available in market for any medical use?
Yes, from Genolite. Right, it is. Yeah, they're putting it into hospitals. Yeah. Yes.
Are there any other kinds of different gold nanostructures they use for the plasmonic enhancement?
Yeah, some people use nanorods, which are rod shaped. Some people use nanoshells, which are gold on the outside and they have glass on the inside. And some people use just solid gold. Okay. Yeah. Sorry. Yeah.
You said in the initial part that the initial ones couldn't detect the MS2. So after increasing the sensitivity, now it helps in detecting the MS2, does it?
Yes. Apparently, just recently, single atomic ions were detected inside of the fluid, right? Not by our group, but by a group in Germany. So yeah, it enhances the sensitivity tremendously. That used gold nanorods, yeah.
Is it possible to distinguish between which virus, say if there's a mixture of viruses in the fluid, is it possible to distinguish which one binds?
Yes, yes. So it turns out what you do is you put specific antibodies on the surface. Now you can generate the antibodies by essentially poisoning bacteria with the virus and then harvesting the antibodies and then binding those to the surface.
Well, I meant at the same time. Is it only for one specific?
No.
At one time?
You should be able to distinguish different things. if you can identify the spatial regions where you put those antibodies. Yes, that's another subject. Yeah, right.
So I have two questions. So the first one is, so for this technology, we're going to rotate the particle. So this particle has to be a hard particle, which means it has to be either polymerized particle or a metallic particle.
Well, the microcavities are dielectric. They're glass.
Yeah.
Because the metals have too much loss, so you don't want to make a solid micro cavity out of metal. It's fine if you just use nanoscopic metal particles. Nanoscopic meaning nanometers in size. But the microcavities we were using were typically 40 micrometers. Okay, so they are 1,000 times the size of those little gold nanoparticles that are put on the surface. Okay,
So
the nanoparticles act as receptors. So if you then put antibodies on the nanoparticles that are specific to a certain virus, then the signal gets enhanced when the virus reaches that plasmonic particle, the little particle, the nanoscopic particle, which is on the microcavity.
So like, what if I use a soft particle, like the hydrogen beads or rose beads or kerosene?
Yeah, I mean, the problem with soft materials for the microcavity is that they will tend to, because their elastic coefficients are not very stiff, they will tend to fluctuate on their surface. That will broaden these resonance lines, okay? And so not as useful, but we've made them out of PDMS, which is soft, and they're pretty good, yeah.
Okay. So the other question is, we know when we rotating the beads, the antigen also like oscillating around the surface. So we know that what if we have the polymerized particle, and then the antigen could like physically absorb it on the particle, on the bead, or the protein.
Yes.
So we enhance the signal, but at the same time we enhance the ability, the physical absorbance to the beads. How do we avoid this?
How do we
Avoid this.
avoid
We
it?
enhance the physical
Okay, so
function of the antigen.
I mean, typically what you do in these systems is you try to block all parts of the surface. You block it chemically, except for the places where you want the receptors to be. You don't want non-specific adsorption. Okay, so you have a problem, you know, I mean, if you have a well-designed surface, okay, so surface science comes into this, then you can block all of the parts of the surface except where you've put your receptors. Okay. Any others? Yeah.
So when you entrap the analyte, when it locates the antibody, is there a difference for perhaps suppose you have another antibody, is there a difference in the rates of locating the antibody on that particle?
Once again, if unless you have a way of the rate will be conditioned by the on compared to off time. So remember, most of these antibodies physically bind, right? The antigen to the antibody. So there's a certain time over which they'll remain there before they come off. There are some things that bind very nicely, like streptavidin and biotin, right? Things like that, very strong. But a lot of things, basically have an on to off rate. So the answer is, yeah. The reason why people would want a thing like this is because they want to test antibodies and see which ones are most effective. The ones that are most effective would have an on rate much greater than their off rate. So you've hit on a very important purpose of this overall thing, to test basically the quality of antibodies for particular antigens. Does that help? Okay. Any other questions? Yeah, go ahead.
So you would want to put the antibodies on the equator just because that's where the flow of the antigen would be?
Well, that's where the light is moving, right? At least in what I demonstrated, right? It is possible by using different frequencies to move the light to different places. But no, the neat thing about this is that what we call that carousel trap, we call it that because it's like a carousel, right? It can draw things to the surface and then they stick at a particular latitude, right? So thinking about the Earth as having an equator, a North Pole, South Pole. The only difference between our micro world and that is that our micro world is only 80 millionths of a meter across and the Earth is 8,000 miles across. But aside from that, the geometry is the same, right? So, yeah. So what you'd want to do is pull the particle to precisely where the light is, and that's exactly what this carousel trap does. It's very fortunate. I hope that helped. Okay. Any other questions? Guys, what's happening here? A guy.
How do you solve the impurity of the sample?
How do you solve?
The impurity of the sample, like you want to test the viruses, right?
Yes.
So you want to test the blood.
Yes.
Blood is kind of like a massive.
Well, okay, let me since that's a very hard question to answer, right? And I recognize that, but I wanted to point out something. Inside of your system right now, okay? And my friend here can tell us just how many interactions are occurring per second with the DNA, right? And there are a lot of impurities in there, right? You can recognize the right protein based on receptors which are in the biological system. So you're depending really on this idea of using biology to create the stickiness of that surface that's specific to particular antigen, okay? And it's pretty selective. Otherwise, you wouldn't be here, right? Think about that, right?
It's a wonderful question, but in practice, I think what happens is that because of in terms of sensitivity, the dilute the cell to a point where it's very manageable. Because of course you don't want to have it wrapped in there. Steve, can I ask you two
I never
questions?
heard of a crap protein.
No.
Right, so, I mean, that's a new.
Do you know the word crap? Anyway.
Who's on first?
The first question is this. Can you go through why the thing is called regarding...
Yes.
Yes.
Yes. I can do that, but I had not done that. So, I'm gonna take us all the way from London to Beijing. Oh, not going to take too long. Okay, so if you go to London and you go up into St. Paul's Cathedral, and it's about one level up, there is a gallery which is completely round. It has sort of concave walls a bit, and if you whisper into the corner, then you can be heard 40 meters away on the other side by a person standing there putting his ear toward the surface. Because what happens is the acoustic wave comes around. So obviously this is not acoustic, right? But it seemed like the right title for it because it was already a phenomenon that people knew. They called it a whispering gallery. Now, I'm going to take you to Beijing. In Beijing, there's a place called the Temple of Heaven. Okay, guys, tell us about the Temple of Heaven. What do they have there?
It's the same like in London.
Just like London,
Yeah.
but much, much larger. Everything is larger in China. Okay, much, much larger, right? And people stand at the wall and they whisper to each other. I think it's more than 70 meters or more across. I mean, it's really incredible.
Can we get back from China to Grand Central so we can go and explore.
Right, but Grand Central is not a complete. Okay, so what happened in Grand Central, I think, and I'm interpreting this, is that Vanderbilt, so man, a wealthy man, gave the property to the people to build Grand Central. But he demanded only one thing, that in the basement of Grand Central there be an oyster bar where he could have his oysters. Okay? The ceiling of the oyster bar was like this. Okay? The story is, whether I don't know if it's entirely true, that he would sit his competitors at one side and he would sit himself on the other because he remained quiet. And that's called a whispering gallery, but it's you might call it semicircular, right? So not resonant in the same way it was. Yeah.
In fact, just before you get into the oyster bar, there's kind of a little...
Just on the outside.
Yeah, a little enclosure outside, which
Right.
is what it was shaped like some little cathedral.
Right.
And every time you go there, you'll see people whispering on one side of the wall and listening on the other. It's much smaller, of course. I guess about 20 foot across. But you can go and try it. That actually works. But the principle still is talking about a way of going around the sphere,
Right.
right?
Well, in this case, around a hemispherical top.
Anyway, that was the first question.
Did I see a hand? Guys, you're still being beat here.
And
There's,
my second, while we're
Wait.
thinking, is can you go through again why the resonant peak is generated in the sphere? So that I can ask
I mean, why it's inverted.
What you are seeing essentially.
Yeah. It's because as the light, one way to think of it is as the light generates the resonance, the energy goes into the sphere and not into the rest of the fiber. That's one way to think of it.
Yes, so essentially, I mean, what we're seeing is that once you get into
We see a
the
dip,
resonance
right?
mode, you have the sphere steals energy from what goes through the fiber, and hence you get a signal. Right? Does that make sense? Very similar to what we talked about last time.
Okay, well, I want to, I can see you've been very participatory, and I thank you for that. Let's a little hand for our professor. Okay, and
Thanks so much, Steve.
sometime